with gas laws, and today we're doing the ideal gas law. Remember, they're going to ask you what is an ideal gas, and you should know that they are elastic collisions, they're small. How does it go? I forgot now. You should know it, but I forgot it. That's not fair. I know that they're small, they're far apart, they're small atoms, the atoms are far apart, and they have elastic collisions. So remember that. You have to understand all of that. No, but just know that there are things that behave well when you're doing gas law equations, and there's gases that don't, but all the ones that we're going to do behave well and are ideal gases. So we learned some gas laws, Boyle's law, Charles' law. We put them together, combined gas law, but that doesn't really tie us in very much to chemistry. So chemistry, we like it when it has to do with our balanced equations, tying them in with our stoichiometric coefficients and our moles. And so now we are going to deal with the ideal gas law. And it is Pivnert. So I knew someone who named their horse Pivnert. Okay, really total nerds, right? So pressure, volume equals this N, which is your number of moles. That's where it ties into real chemistry, your number of moles. And then R is a gas law constant, and we're going to have to memorize that one. And it is, so R is a gas law constant. Let's use red because it works better. 0.0821, and kind of seems like a pain to memorize this unit, but if you remember the unit, it will help you set up all of the rest of the equation. So it's liters, atmospheres per mole, Kelvin. So liter, there's your volume, so your volume is going to be in liters. Your atmosphere, there's your pressure, so your pressure is going to have to be in atmospheres. So mole, that's your N for your number of moles. And Kelvin, which when you're doing gas laws, all of your temperature has to be in Kelvin. Okay, so we're going to use Pivnert. Again, this is the gas law constant. You have to memorize it. 0.821 liters atmosphere per mole Kelvin. Okay, so let's do example 12.5. Example 12.5. So let me just scooch this over. So let's write it this way. PV equals nRT. So as we read our question, we can fill in what we don't know to solve for, or we can fill in what we know to solve for what we don't know. So example 12.5. A 12.2 liter container, so there's a volume, 12.2 liters, is at a pressure of 13.5 atmospheres at a temperature of 25 degrees C. Uh-oh, we're going to have to do something there. How many moles of the gas are present? Well, we know R because we're going to memorize it. 0.821 liters atmosphere per mole Kelvin, which tells me what all of my units need to be in. Fine with liters, atmosphere, I'm fine with moles because I'm going to solve for moles, but I need to always change my temperature to kelvins. So you're going to add, does anybody remember to add to make Kelvin?
273.15.
Very good, 273.15. Hi, welcome. So most of the time you don't have to remember the 1.15 because when you're adding and subtracting significant digits, you're going to round to the least significant place. So I'm going to get an answer there, right? And 0.1, 1 rounds down. So if you have a number that doesn't have anything in the tenths place, you can just add 273. Okay, so if I add 25 and 273 and 25, I get 298 Kelvin. Okay, Alyssa, we're talking about the ideal gas law that you're going to memorize. All right, so PV equals nRT. So PV equals nRT, Pivnert. So we're going to solve for N because we want to know the number of moles. Again, this is where it's tying into real chemistry. So I need to divide this side by RT. Hopefully you know how to rearrange an equation, which means we can cancel these out, which means I have to divide this side by RT, and then I solve for N. So I'm going to just drop in everything and solve for N. So I'm just going to rewrite it so N's on this side. So my pressure is 13.5 atmospheres. My volume is 12.2 liters. And my gas constant, which you've memorized, is 821 liters atmospheres per mole Kelvin, times my temperature in Kelvin, which is 298 K. So again, it's a pain to memorize it, but once you memorize it, you can make sure all your units cancel. So this atmosphere cancels out that atmosphere, this liter cancels out that liter, this Kelvin cancels out that Kelvin because it's on the bottom of the bottom. And when you're dividing fractions, right, it's this mole is on the bottom of a fraction. When dividing fractions, don't ask why, flip that sucker and multiply, right? So what happens is that mole flips up. So your unit is going to be left in moles, okay, which is what we're asking for. How many moles is this? So order of operations, make sure you use your parentheses. So you're going to do 13.5 times 12.2 divided by parentheses 0.0821 times 298 and parentheses equals. Okay, so make sure you don't hit divided by 0.0821 times 298 and not use parentheses because that makes your 298 come up here and you don't want that. So either figure this out first and write the number here, or when you're dividing, hit the parentheses. Okay, so order of operations. If you write it down though on your test and you do the calculator wrong, I only take a quarter off, just so you know. Okay, so what does that give you? It gives you 6.7318 blah 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 moles. But here I have three significant digits, here I have 3, here I have 3, here I have 3, I can only have 3. So 6.73 has to round to this place. This is a 1, so it rounds down. So my answer is 6.73 moles. Okay? So again, why do I care? I care because this is how it's going to tie me into moles, which is really talking about chemistry. Okay? All right, so we are going to do an experiment today. Did anyone bring a 2-liter bottle? Oh, you're all fired. Okay, so I have one 2-liter bottle and I have a wine jar. Okay, so now we know what do the colleagues use more, not soda. Okay, so it should work. So you can maybe work in 2 groups then, since I only have 2. So basically vinegar and baking soda, right? We're going to mix some vinegar and some baking soda, and we've done this before. Last time we did this learning about when it runs out, right? The limiting reactant. So today we're not going to worry about the limiting reactant. They're going to tell you in advance that the baking soda is going to be your limiting reactant. So what we're going to use it for is to do our ideal gas law. So I wrote up, thank you, Mrs. Pollock. That makes it so much easier for me. You're welcome. This is how we're going to follow along. And then when you're done with the lab, we're going to work through the problem together, putting this gas law into practice. So the things up at the top are what you're going to need to measure, but you still need to follow along in experiment 12.1. So this is your results, but you still kind of need to write me a description and a conclusion. Okay, why do I care? That's your conclusion. Why do I care? Why are we doing this? And probably your title, using the gas equation to determine the amount of acid and vinegar, probably should be in your conclusion. All right. So we'll do this together. So you're going to need to figure out the mass of your vinegar. You're going to need to know the room temperature in Celsius, which we'll just look at one of our things down here to get our room temperature. And today's atmospheric pressure, I just asked Google, is 0.99 atmospheres in Columbus today. So we'll use that to factor in. And we'll work through this together at the end. So follow your directions, and I have 3 set up over there. Use whichever ones you want, and let's go. So we put some vinegar and baking soda together, and we filled up the balloon, and we measured the circumference of the balloon. This is going to pop off at me. Okay, so let's figure out the rest of our numbers here. Atmospheric pressure, again, is 0.99 atmosphere today in Columbus. The room temperature today is, here you go. You want to read that for us?
20 degrees Celsius.
20 exactly. I think you can read one more place. Or that's the number. So yes. Also 20.5?
Yeah.
Okay. 20.5 degrees Celsius. Okay, and we know R is 0.0821 liters atmosphere per mole Kelvin. All right, so we're figuring out N. And volume, we're going to have to figure out volume. But you should have, okay, so what else is on here? You have your mass, just for Amy who's gone. Mass, what did one of you have for your mass of your mass of vinegar? 200.0? 200.00? You should have been able to read it to the hundredth, so.
Sure.
Okay, measured exactly, 200.00 grams. And the circumference, CIRCUM, circumference of the balloon was, anyone? 61.50.
Yep.
Centimeters, not inches. Okay, so here's the reaction that happened. It's acetic acid and baking soda. We're going to rearrange PV equals nRT so that you're solving for N. So maybe you can practice doing that there on the side, solve for N. So remember, PV equals nRT, so I'm going to divide this side by RT, which means I divide this side by RT, which means I'm left with P times V over R times T equals your N, which is your number of moles. All right, so we need to, temperature is easy. So our temperature is 20.5, so we need to add 273.15. So 273.15, we're going to get a 0.6 here, but 293.65, and we have to round to my least significant place, so that rounds that up to a 7. So 293.7 is going to be your temperature. All right, so volume is the tricky thing, and this is not something that's going to be on your test, so hopefully you have done some geometry. This is more geometry. We figured out we have the circumference. Now let's just take into consideration this should be a perfect circle. It's more oblong than that, so we're going to pretend it's a perfect circle. And so if it was a perfect circle, circumference equals 2 times pi times r. Okay, so if we solve for our radius, that equals the circumference, which is what you measured. So we're going to use 61.5 centimeters for here. I'm solving for r, so divide by 2 pi. 2 pi. So you should get a radius of, I don't know, anybody get that? Well, yours might be a little different, right? Whatever yours was. 61.5 divided by 2 pi, 2 times pi. So this is 9.788, and I have 3 here, and this is like an exact number, so 3, so 9.79 centimeters. Okay, so you could be filling your thing out here. All right, so before we find the volume, we have to change the units a bit so it's a more useful unit. Again, you're not going to have to do this on your test. This is just for our lab experiment here. So we're going to take our 9.7 centimeters or whatever yours was, and we're going to multiply it by 1. There's 1 decimeter and 10 centimeters. I don't know if that's something you memorize, but it is. So we're going to divide by 10, which means I get 0.979 decimeters. Why do I want to do that? Because our radius has to be in decimeters, so this works out. So we're going to use that to figure out what our volume is. And again, I'm not going to have to do this on the test, so don't freak out if you're not following along exactly. But I have the formula here on your lab. So it's the formula of volume of a sphere. Again, we're assuming that that's a sphere. We know that it's not exactly, so it's okay. It's going to be 4/3 times pi times our 0.979 decimeters, and that has to be cubed because it's 4/3 pi r cubed for your volume. And so let's figure out what that is. 0.979 cubed times 4 divided by 3 times pi. Anybody get a number? This one is 3.93 decimeters cubed. Okay? Anybody else get that? Or your number might be a little different if your circumference was a little different. Okay, so that's what we're going to use. As it turns out, cubic decimeters, this is why we did it, cubic decimeters is the same as a liter. So we can just change that to liters, and that's going to be your volume. So that's 3.93, or whatever yours turned out to be, liters. Okay? Did I lose anybody? That last couple math things is more geometry, but it just gets us a volume. So most of the time in your questions in your test or in your workbook, they'll all already give you your liters, so you don't have to worry about converting that. Okay, so what do we have? So remember, last time we learned about partial pressures. So you should be able to find the temperature of the volume of gas. We did that. We need the pressure. So to figure out the pressure of just the carbon dioxide gas, because it's collected over water, because there's water in the air that we use today. Obviously, there's a lot of water in our air today. We're going to have to figure out the partial pressure of that. So we go to our little charty chart, which is, let's see, table 12.1. So at what was our temperature? Our temperature is 20.5 degrees. So at 20 degrees, if you take it from 21 degrees, I don't care what it is. Those are pretty close. But if you took it from 20, actually, 20 is fine. So this is in torr. So we're going to, let's see, pressure to make sure that we have. So we have partial pressure of water in atmosphere from the chart. So we have 0.99 atmospheres. Let me make sure I'm taking the right numbers here. Minus, I'm going to do, I didn't have a place to convert this. I thought this chart was in atmosphere. It's just not, it's in torr. So we're going to have to say 17, I'm going to do it at 20 degrees. 17.5 torr times, in 1 atmosphere, there's 760 torr. So I have to divide 17.5 divided by 760 equals 0.233 atmospheres. So that's the water. This is our atmosphere today. So you're going to do 99 minus 0.23 gets you 0.9. No, it's going to be the partial pressure of carbon dioxide. Remember our partial pressure thing? Pressure total is going to be your pressure of your water plus the pressure of the carbon dioxide that's in our bowl or our balloon. So if the pressure of the water is 0.230 atmospheres and the pressure total is 90.99 atmospheres, if I subtract, that equals that plus the carbon dioxide. So I take that, subtract that, which is what I'm doing here, and that should, minus pressure of the water. That should equal your pressure of your carbon dioxide. So your pressure of your carbon dioxide should be 9.9, I subtracted wrong, 0.99 minus 0.23, 0.76. Is that what everybody else got? So you should have 0.76 atmospheres. Did I lose anybody? Pressures? That was from last week. Okay, so that should be 0.76 atmospheres. Then we finally have this. This not pressure of the carbon dioxide. That was pressure of the atmosphere. 0. It's not working. 0.76 atmospheres. So we should be able to do, I'm not going to erase that. All right. So we should be able to, if we rearranged PV equals nRT for N, we should be PV over RT equals our pressure, 0.76 atmospheres, times my volume, 3.93 liters, over the R, which I've memorized, 0.0821 liter atmosphere per mole Kelvin, times my temperature, which I calculated to be 293.7. I only have two significant digits here, so my answers can only be 2. So what's that? 0.76 times 3.93 divided by parentheses 0.0821 times 293.7 and parentheses equals 0.123869. I only get 2, so I'm going to get a number here, which means I look at this one. 0, 1, 2, 3, 4 rounds down, so, and my unit is mole because liter cancels, atmosphere cancels, Kelvin cancels, and my mole flips up. Okay, so I have that many moles of acetic acid. All right, so for every mole of carbon dioxide came 1 mole of acetic acid. So how many moles of acetic acid did you get? Well, you have to convert. So if you do 0.12 moles of C2H4O2, which is your acetic acid, and you it says grams, that's why. So then there are 60.0 grams and acetic acid in 1 mole. If you look at your periodic table and you do 2 carbons plus 4 hydrogens plus 2 oxygens, you should get 0.12 times 60, so you have 0.72 grams of acetic acid. Now, if you take that over, divide that by the grams of vinegar that you had, the whole you all had what, exactly 200, I erased it, right? Like 200.00, was that what it was? So let's find the percentage. 0.72 over 200 equals 0.0036. So to make that a percent, you would do 0.36%. It actually should be closer to 5%, but because if you look on the bottle, it'll say 5% vinegar. So if we did all our calculations correctly, it should have been close to 5, but it's not. So why would we get a difference? Well, our moisture content might have thrown off the number from the chart because it's 100% moisture outside. Our bottle is not an exact circle. That could have thrown it off. Maybe you didn't measure quite exactly if it wasn't 200.0. Maybe my vinegar is old and it doesn't have 5% vinegar left in there. Not to throw you under the bus, but when you measure back and forth, if you had water in the bottom of your thing and then you put it back in the vinegar, it may have diluted that. So, okay, but what have we learned? Can we figure out how many moles using the ideal gas law? Yes, we can. So PV equals nRT. Make sure you can rearrange it. We kind of use the partial pressure thing. That's going to be on your test. Don't worry about calculating area or volume of a circle or anything, but fill this out, write me a conclusion, write me a description, turn that in for next week. All right, it should be, again, this should be close to 5, but it's not. All right, let's do example, I still have 15 minutes. Let's do example 12.6. All right. One way hydrogen can be produced commercially is to react a strong acid with a metal. There's your hydrochloric acid, and zinc gives you hydrogen gas and zinc chloride. If 512 grams of hydrochloric acid are reacted with an excess of zinc at 24 degrees and pressure 90.95 atmosphere, what volume of hydrogen gas will be produced? Doesn't seem like we have enough information there, but we do. So let's see which one's going to work well for me today. All right. So, well, we have, let's go through and see what we know. We have 512 grams of HCl. We have excess zinc, so we don't have to worry about that. We have a temperature of 24 degrees C, and we have a pressure of 0.95 atmosphere. R, we always know 0.0821 liter atmosphere per mole Kelvin. What volume will be produced? All right, well, so remember, if you memorize your gas constant, this has to be in liters, which, fine, that can be in liters. Atmosphere is already atmosphere. Moles, oops, we're not in moles. And K, it's not in K. So that one's easiest. So let's add 273.15. Who cares? Because this is going to be rounding to the least significant place. So 24 gives me 7, gives me 9, 2 gives me 2. 297K. All right, so then we got to convert this to moles. So, how do we do that? We're going to multiply such that my grams cancel out and my moles are on top. Where do I get my grams? My handy dandy periodic table. I'm going to look how much hydrogen weighs, how much chlorine weighs, and I'm going to find out how much 1 mole of hydrogen chloride is. HCl, HCl. And so if I add those two things together, I get 36.5 grams of HCl. So then if I take 512, and I divide it by 36.5, I get, why is it doing that? I get 14.0 moles of HCl. So here's my problem. That told me how many moles of HCl I have, but I want to know when in the end what volume of hydrogen gas will be produced. Well, darn, that's not hydrogen gas. So I have to look at my balanced equation. I didn't write it down here. 2HCl plus zinc turns into H2 gas plus zinc chloride. So I figured out how many moles of HCl I have, but they want me to know about how many moles of this I'm producing. They told me that's excess that. So how do I go from here now to here? That's back a couple chapters. So remember, these stoichiometric coefficients tell me for every 2 of this, I make 1 of this, or 2 of this mixed with 1 of this gets me 1 mole of that and 1 mole of that, because it's a balanced equation. So if I know that I have 14 moles of this, how many moles of hydrogen gas am I going to make? Well, I have to do, I'm too lazy to rewrite it, so I'm going to do 14 moles of HCl, and it's going to be a ratio from this balanced equation. I want my moles of HCl to cancel out on the bottom, and I want to go to moles of H2 gas on the top. So for every 2 of these, I'm going to get 1 of these. So I'm just going to divide this in half. So 14 divided by 2, I can do that in my head. 7.0 moles of H2. Okay, did I lose anybody there? Actually, they gave me 2 significant, I guess I do get 2 because I've got 3 there, so I should have 3 here. Okay. So now my N is really 7 moles of hydrogen gas. Now can I figure out the volume of it? Yes, I can by PIVDIRT. PV equals nRT. And I'm going to solve for V this time, which means I divide by P on this side so they cancel out, which means I divide by P on this side. So I should have volume equals my number of moles, 7.00 moles, times my gas constant, 0.0821 liters atmosphere per mole Kelvin. Again, I write it out so I can see that my units cancel. T is going to be 297 K divided by my pressure, which is 0.95 atmosphere. Everything cancel. This mole cancels this on the bottom because it's on the bottom of this. This K cancels this K because it's on the bottom of that. This atmosphere cancels this atmosphere because this is on the top and this is on the bottom of this fraction. And so I'm left with my volume in liters. Was that what I want? What volume of hydrogen gas? Didn't say, but that's going to be fine. So this one, you don't have to worry too much about order of operations because it's just this times this times this divided by this. You don't have to worry about parentheses. So 7 times 0.0821 times 297 divided by 0.95. And I get why just my thing is not in the right. Let's try this again. 7. Oh, that's why, because I looked at the wrong problem. 7 times 0.0821 times 297 divided by 0.95 gets me 180 liters. This has got 3, this has got 3, this has got 3. This only has 2, so I only get 2 significant digits there. Okay? I still have a few minutes. Don't shut your brains off. Did I lose anybody? Write down what you know. Figure out the one you don't know. Rearrange your equation for whatever that is, PV equals nRT. Rearrange your equation. And then just drop everything in, making sure that your units cancel. Okay? They are going to throw a couple in there, at least one, that they're going to give you grams of something, and you're going to have to remember back a couple chapters ago how to go from grams to moles, from moles to moles on the balanced equation. And then probably this next one, I think you have to convert back to grams. So let's do that because that's a little evil. All right, so let's practice. All right. If 4.5 liters of water vapor, okay, so liters is volume, 4.50 liters of water. Oh wait, so I should write down the equation here. We have 2 waters, moles of water plus Mg magnesium turns into magnesium hydroxide and hydrogen gas. If we have 4.5 liters of water vapor, 4.50 liters, we'll just write it there, at 200 degrees C, 200.0 degrees C, my zeros never look like zeros, they always look like sixes, sorry about that. And 4.94 atmospheres are passed over excess magnesium. How many grams of magnesium hydroxide will be produced? So this says excess, we don't have to worry about that. So what are we doing? We know that we have this many liters of this. Doesn't seem like it seems like I'm missing something. How many grams of magnesium? I want to know how many grams of that is. So let's see, do I have all the things? 4984, 5 liters on 200 degrees. All right, so that doesn't tell me how many grams I have. So let's figure out how many moles of water I have. So if we have, this one is 0.0821 liters atmosphere per mole Kelvin. I've got to first figure out that of water and then convert to that. So remember PV equals nRT. I'm going to rearrange so that I get my N by itself. So those cancel out. So that equals my pressure, 4.94 atmospheres, times my volume, 4.50 liters, over 0.0821 liter atmosphere, mole Kelvin, times temperature, plus 273.15. Ooh, that's really hot. 400, nope, 473.1, well 2, because it's going to be 15 and I'm going to round it to this place, right? All right, times 473.2 times K. So you're going to put that in your calculator, 4.94 times 4.50 divided by parentheses, 0.821 times 473 end parentheses, and I should get a number of moles at 0.572 moles. Okay, so that tells me how many moles of this I have. 0.572. But they didn't want that. They want to know how many grams of this I have. So now I have to go back in my brain and remember how to go there. So remember, if I have 0.572 moles of H2O, I'm going to do a ratio from the balanced equation. For every 2 moles of water, I get 1 mole of magnesium hydroxide. But I can't stop there. I mean, you can do it, but I would just keep going. I want to get rid of my moles of magnesium hydroxide and go to how many grams of magnesium hydroxide I have, so that my final answer is going to be in grams of magnesium hydroxide. So I have to look on the periodic table and go 1 magnesium plus, this is 2 times oxygen and 2 times hydrogen. And that is 58.3 grams of magnesium hydroxide and 1 mole of magnesium hydroxide. So you can do this in 2 steps. I'm lazy and I don't want to write it again. So 0.522 divided by 2, that gets you into moles. And then you divide that by, or multiply it by 58.3 to get you how many grams of magnesium hydroxide you have. And it should be 16.7 grams, because you have 3 significant digits there, so your answer can have 3 significant digits. Okay, so this is how it ties into chemistry. Okay, and this is back a couple chapters, but I know you can do it. Okay, and filled up the entire time. All right.